So, what type of projections do we use in engineering? So, we divide them into two categories, parallel and perspective. Parallel is the ones that are used in engineering. Perspective is the one that is not used in engineering, typically used in architecture or art, and that's the way our eyes would see the real world. So what's the difference here? The lines of the object, the edges of the object that are parallel in real world, when you project them, when you show them, you still show them as parallel, right? So look at this line and this one and this one and this one. They're all parallel in real life, and when you project them in an isometric projection, you show them as parallel. But here, if you look, they do not. Instead of them being parallel, they actually converge to one or several points. We call these points vanishing points, and that's the way our eyes see the real world, right? So probably if you see railroad, right, in real life, you see that these two rails, although being parallel, when you watch them or you take a picture, it appears to you that as they get further away from your eyes, they get smaller and smaller, and the lines would converge, right? So as I said, in engineering, we don't use these because to us, if an object is 5 inches long or 10 inches or a meter or 2 meters, it doesn't matter if it's right next to me or a mile away from me. It's always the same, and we try to project it that way too. So we do not use perspective. I'll mention it, I briefly go over it, but that's not the type of thing that we engineers use. We use parallels. Now, parallels, there are two groups, orthographic and oblique. And I'll go over oblique a little bit, but we mostly use orthographic. And orthographic, again, there are two categories. There is a category for axonometric. The other one is for multi-view projection, multi-view orthographic projection. And these are if we want to show one single view of the object and render the object like a 3D shape. So although we draw these shapes on a single 2D piece of paper, but the way we draw it, the object appears to be 3D. Okay, so the most common one is this that we're going to work on today. It's called the isometric. There are other types too, like dimetric and trimetric. Again, I mentioned them. We don't go through them, but we focus mostly on isometric today. Now, as I said, showing this to a manufacturer is not enough, okay? It gives an idea of how the object would look like, but not relevant information like dimensions, tolerance, and so on. So when we want to communicate to manufacturer, we need to create these guys, multi-view orthographic projections, and we'll do that later as well. But as I said, this right section is engineering, the left section is art and photography and architecture. So let's go through them and learn about the details. So you can see here, for example, another example is a stapler in parallel projection versus what? Perspective. Now, as I said, the one that we want to focus in this lecture is isometric. So we render the object on a piece of paper, we render it like 3D. How? So the way we do it is, we have three axes, right? X, Y, Z, let's say. And we have to draw these three axes on a flat piece of paper. So how do we do it? So we draw the y-axis or the height axis completely vertically upward, just like we do normally. And then x and z will be at 120 degrees with respect to y. So the angle between all axes are, all the angles are 120. Or if you continue this x-axis on the opposite side and continue the z-axis on the opposite side, which are these two lines, this one and this one, then the angles of these two axes with respect to a horizontal line, if you draw, will be what? 30 and 30. Okay? And 30, where does it come from? It's 120 minus 90 degrees, right? So if you draw a horizontal line from here, correct, and continue the z-axis, then you have 30 degrees. So again, 30 degree x, 30 degree y, z, I'm sorry, and 90 degrees y, all with respect to a horizontal line. And again, y is for the height, x is for the width, and z is for depth. So let's say if we want to draw a cube, how do we do it? So a cube has 6 faces. We cannot show all 6 faces, so what we do, actually we only show 3 faces out of the 6. Which 3? So we show the front face, we call this face front, this one right, and that one top. We cannot show the left face, the rear face, and the bottom face. And when we do isometric, although here the edges of those 3 hidden planes or faces are shown with dashed lines, but we never do add dashed lines for hiddens in an isometric. So they are just here for information. But when we do later, when we do an isometric, so this is an isometric of a cube, we never add the hidden lines to an isometric, okay? And I have mentioned it in one of the future lectures, but you know what? Let me formalize it here and make sure that everything is completely understood, okay? Because I do not want anybody to miss on anything. So let me do something for you before I move any further. So this is the height axis. Okay, so y is me expand it. Y is the height. And then we have z to be depth, and we have x to be what? Width. Okay, so just knowing which one is which. And also I add this thing for you here that never show hidden lines on an isometric view. Okay, this is extremely important. I want you to always observe this and follow the rules, okay? Never ever show that, okay? That's not the right thing to do. There we go. So that's what I want everybody to focus on. And I put one more of that for you here so that you do not forget. Okay, so we got this. Now here actually we don't need, let me get rid of that. So now, why do we call it isometric? What does that mean? Iso means one and metric means measure. So isometric means there is one measure or one single scale on all 3 axes. So for example, if I use a scale of 1 to 1 on the x-axis, I use the same for y and the same for z. We typically use 1 to 1 unless there is a reason, but we use 1 to 1 on all 3 axes. And since there is one scaling on all 3, we call it single scaling or isometric. So now, let's say I want to first draw a cube Very simple. Draw a cube, and this cube is basically 7 units in width, 3 units in depth, and 4 units in height. Okay? So, first of all, you might say, what is this guy that is in the background? This is called an isometric paper. So this isometric paper is what you draw your isometric views on. And on this paper, you see there are vertical lines, and then there are lines at 30-degree angle. So this is something you can easily draw isometric on. Do not draw them on blank papers, because then you have to draw all of those 30 degrees. Where can I find one? On Canvas. If you go on Canvas under Modules and go down under Assignments, there is this file called Isometric Sketch Paper. So you can easily download, print, and draw whatever you want on it, like homework 1, and then take a picture of that and upload it here on Canvas under Assignments, right? So Assignment 1, homework 1, is the first part of it is drawing isometric papers, right? Isometric views, I'm sorry. So if you go here, you see here the views are given, and you have to create the isometric view. And this is an isometric paper, but if it's not big enough, then you can, instead of doing it on this paper and printing this and doing it on this, you can go and get it from here on Canvas under Modules Assignments, do them on this paper, and then take a picture of that along with this part, which is for your next lecture, creating multi-view orthographics from an isometric, which we'll do in the next lecture. And then once you have the picture of all of these, then you upload it as a single file, PDF, or if they are pictures, you can put them in a zip folder. And then you will submit all of them on the same location. So when you click here, it gives you a Dropbox, and you can upload your zip folder with the name of the folder to be your name. So here, I got that paper here, copied it in my OneNote. And now, as I said, I want to draw a cube. And this cube is width of 7 units. And then we have a height of 4 units. And then we have a depth of 3 units. Okay? So I want to draw such cube here. How do I do that? So a cube is the simplest thing that you can draw in isometry. So I start at any point that I want, preferably in the middle so that there is room all around it. Don't go to the corners and then go to the left, you get out of the paper. So I start here, it doesn't matter. And then from this point, remember this direction here is depth, right? Z. This direction here is what? Width, or X. And this direction here is what? Height, or Y. So from here, in the height direction, I move 4 units up, so I come here. By the way, it is really hard to draw with a pen on a monitor. So if you see my handwriting or lines are not good, that's the reason, okay? It's not as convenient as writing on whiteboard or a piece of paper. Then from this, I go 7 units in the width direction. So you count 1, 2, 3, 4, 5, 6, 7, right? So you connect. And then from the same point, you go 3 units in depth. Yes, you see that? So 3, 4, and 7. And then from these points, you repeat. So from here, you go 3 units in depth. And then what? 7 units in width. And then from this point, you just go up 4 units in height. From this point you go 4 units in height. From this point you go 3 units in depth, and connect these two with 7 units in width. There we go. That's your cube. Okay, so this is how you draw a cube with given dimensions. Now, not always the isometric is as simple. Sometimes you have an object like this. So if you want to show this, how do you do it? So here the coordinates of the vertices are given except for one point. So the basically back corner here is at origin. And then if you draw a box here, you can see that if you look at the x-axis, the max dimension is 7. If you look at the depth axis, z, you see is 3 and height is 4. So it's 7 by 4 by 3, which is exactly the same cube that we just made, okay? So what is this cube? We call this cube a bounding box for this object. What does that mean? Means you can put this object completely inside this box, yet this box is the smallest box you can do such a thing with. If you make it any smaller, then this object would stick out of the box. If you make it bigger, then there are some loose space, right? So a bounding box is the smallest box that completely contains the object, and some of the faces of that are touching what? Some of the faces of your object, okay? So first thing we do when we are given an isometric like this, we draw a bounding box for it. We count the max dimension in each one of the axes, along each one of the axes, and we draw a bounding box. Yes? Then we'll try to locate different vertices, okay? We'll try to find these. So if you call this 0, 0, 0, then if you go 4 units up, that's next one, this is next one, and so on. So here the coordinates of all points are given except for one point, and I'll show you later how to find it. The problematic corner is this one. Okay, that corner there is no coordinate for it. One of the coordinates is missing. So if you look, the width of that is 3, the height of that is 4, but the depth of that, which is the length of this line from here to here, this line, that is not given, and I'll show you how to find it. So another thing that you have to do, and let me copy this picture. Another thing that you have to do, which you don't have to, but I recommend, is basically give a name to each one of the planes or surfaces that you see here. So let me go through steps and tell you. So let's see where I can. So if I add this here for you, where is a good place? Maybe here, it doesn't matter really. So I give a name to each one of the faces that I can find here. So I call this face A, I call this one B, I call this L shape C, this guy here D, this one E, and this small one F. So there are 6 faces. If I can draw them, my isometric is over, right? Now, how do I do that? So remember your origin. Now here your origin is not this guy, it's the back origin. So your actual origin is here. If you go 7 and 3, it's here. Okay, so this point is 0, 0, 0. That one with green, right? Or not actually here. This one. I'm sorry. It's this one. So now, how do I do it? So there are 6 faces, and you start to find the vertices of one of these faces and connect them together to draw the face. Now, which face is the easiest to start with first? Among the 6 faces, which one is the easiest? The answer is the face or faces that are touching the bounding box. Like A is on this front plane, B is on the top plane, and F is what? On the right plane. So A, B, and F are my nice planes. I would first go to these guys, then if I can, I go to C, E, and D. So now let's look at A, for example. Where is A? So if you look at A, this corner of it is the bottom left corner of the object, so it's here. Then you go 4 units up, right? You go from 003 to 043. So you go 4 units up and go to this corner. From that, you go to here, or you go down here 2 units, right? Just compare the coordinates. And then this is the next one, correct? And when you connect these 4 edges together, 4 vertices together, right? So here, that's one. Let's see. This is 2, this is 3, and this is 4, and you can call this what? A. So A is done. F, if you look, this corner of it, this bottom right corner, is the bottom right corner of the box, and then the dimension for it is 1 by 1. So this guy here, if I draw it, this guy is F, right? Now B, I have this edge of it determined. This is the top edge, so that is this side of B. This other one goes from 040 to 34, so it's 3 units, so that comes to here. Now, when you want to draw this edge, you don't know how far you should go. You don't know where you should stop, how many units. It's somewhere between 0 to 3, but how much? I don't know, because as I said, the coordinate of this point is what? If you see, since this is a flat plane, horizontal plane, the y of all points is 4. Now, also, if you look at plane D, it has a constant x number, and that is 3. So this guy is 3, 4, and the z is unknown, and z is this depth here. So now the question is, how do we find that? So in order to do that, we need to look at plane C, this L-shaped plane, which is a type of plane that basically is perpendicular to the top plane or the bottom plane. So when you look at this plane from the top, basically all you would see is an edge. Okay, so if you look at this from a top view, basically if you look at this body from the top view, you would see something like this. Okay, and then this guy here just keeps going like that. So this plane C will be an inclined edge when you look at it in the top view. Okay, and any edge on this plane C, the ones that you can see, this one, and this one, these 3 edges, these are all parallel to each other. So what does that mean? Since isometric projection is a parallel projection, so I can use that property. Well, at the moment, I can draw this bottom edge. Okay, the bottom edge is completely doable to draw because I know the 2 endpoints, right? So it goes from this point here to this point. So this is the bottom edge. Now this top edge here is parallel to that, so I would draw a parallel line to this line from this point. So I draw a parallel like this. So this one and this one are parallel, and then I continue this line I know the endpoint is on 3 units of width, so I continue this. And wherever they intersect, which is here, somewhere between 2 to 3, that is the actual depth of the point, okay? And mathematically, I can show you how to find that. And one time I calculated, it was like 2.6 something, several decimals. But we don't really need to do that. So as long as I know how to find the coordinate of that, that's enough for me. Okay, so now that I got that, and this is plane B, now I can, so I got the 3 planes touching the bounding box. Now I can go over D. If you look at D, so this is height 4, and this point here, which has the same height as this one because plane E is flat, horizontal, so the height here is 1. Okay, so this point is 3, 1, and 0. So you need to go down 3 units in depth like that. So from here, basically, I would go down 3 units, something like this. And then from here, I do the same thing, 3 units down. And I connect them together. And guess what? This is your plane D. Now, if I just connect these 2 edges together, these 2 vertices together, now this L shape is C. And if I connect these 2 vertices together, this one is, and I got my object. And now the last thing you need to do is to clean any line of the bounding box that does not overlap with the edges of the object, okay, or it's hidden. So I take up my eraser. In your case, if you want to do it on the paper, I suggest you draw the bounding box using pencil, and then maybe use pen to draw the object over that, so later you can clean up the rest of the bounding box with an eraser. Okay, so clean that up and it will make life very nice and easy for you. Okay, so here we go. Okay, so this is how you would create an isometric. First bounding box, then the faces of the part that are touching the bounding box, and then the rest. So this is one practice for drawing isometric. Okay, and here you can go through steps. Now there is another one here, and I can do this one as well. Let's actually do it. Just since you have enough of practice, then when we come to class, I'll give you more problems to practice on. But if we want to do this one, so let me create a new page, and then let's see if I can copy my isometric over here, if it allows that, hopefully. There we go. So that is my paper. And then I need this with all of the coordinates. So let's grab that as well. And then we go to OneNote. Okay, so here we go. That's our object. So first we need to draw a bounding box, and if you look at the size of the bounding box here, you see that it is 6 units width, 6 units right, so this is 6, this is 6, and you go from 0 to 4, so that is 4, so you go 6, 6, and 4, so you start anywhere that you want. Again, it does not matter. I start here, you go 6 units in the depth. I go 6 units in the width. And then I would go 4 units in the height direction. And then I create my cube. So 4 units up, 6 depth, 6 width, I'm sorry. 6 depth, 4 height, and again a couple of more lines, and you will get your bounding box. Okay, so that's the first step. Then again, as I said, let's name the surfaces you see here. So here we go. That is A, this is B, this is C, this is D, this is E, and this is F. And then you want to start with one of these. Which one is the easiest? The one that is touching the bounding box. A is on the top surface, E is on the front surface, and F is on the right surface. So any of them would do the job. So if you look at A, that corner of it is this top corner. And then if you look at the units, so you're going from 040 to 043. So the only coordinate that is changing is this guy. So it's 3 units. Similarly, when you go from this to this, again, the only one changing is this. So it's 3 by 3 right triangle. Okay, so I draw a 3 by 3. And then I connect. And this is plane A. If I want, I can do E. So E, you start at this corner. And then as you can see, you go from 006 to 026. So you go 2 units up. This goes all the way to this corner we started with. This here goes from 026 to 326. So the coordinate changing is 3. So it's 3 units. This one goes from 606 to 616, so it goes up 1 unit. And then the diagonal one connects them together. Like that. And this is E. F is very similar to that on the right side. So this is going to be F. Now we can do the rest. So B is very easy. If you see, B has 2 of the vertices shared with A. The other 2 edges are just going down 2 units, right? You go from 4 to 2. So from each one of these vertices, I go down 2 units. And I connect. So this is B. If I connect these 2 vertices of E and F, I would get D. So this is D. And if I connect these vertices of E to B and F to B, then this is going to be plane C. And then, as I said, I get rid of the lines of the bounding box that I don't need anymore. There we go. That's our object. Okay, so drawing isometric with a few practices could be actually a very easy job once you know the coordinates and you have your paper. It's just finding the vertices and connecting. Okay, as I said, we'll do more practice in the classroom, and I have gone through these steps too. Now, one of the things that will happen with isometric is circle. When you have a circle, because the axes of the isometric are not traditional XYZ that are perpendicular to each other, they are at 120 degrees, your circles would deform into ellipses, right? So for example, if you have this can of soda, this top surface that is actually a circle, when you show it in isometric, you would have an ellipse. And you can see here, these are ellipses on the top right and front surfaces of a cube. Actually, the cube themselves, if you look, each surface of this cube is actually what? A square, right? But now, if you look at each one of these squares, how are they projecting themselves? If you look, they are parallelograms, right? Or rhombus. So the squares would be converted into parallelogram or rhombus, and circles go to ellipses. Now, how do we draw an ellipse accurately? So here, let's say I want to draw the ellipse, which is the circle actually, on the top face of this cube, right? How do I do that? So the first thing you need to do is to draw this bounding polygon, this rhombus, that is tangent from all sides to the circle, right? So this rhombus that you see is actually this top surface here. And these angles are, of course, 30, 30. Then what? Then you connect the, or you draw the diagonals, the minor and major, basically. Then you also find the midpoints of each one of the four edges. And then you connect the two ends of the short diagonal to the midpoints in front of them, right? So you connect B to D and F, and you connect A to what? C and E. And then these lines that go from B to D and B to F, they would intersect A to E and A to C at 2 points. We call them G and H. And G and H are on the major diagonal. And by the way, G and H, they have a name for an ellipse. When we draw this ellipse, G and H are called what? You're right, they are the focal points. They are the focal points of the ellipse. So now how do we do that? I use a compass here because I want to draw actual circular arcs. I put the center, the needle of the compass at point A, the center of the arc. And then I use a radius of either AC or AE centered at A and draw this arc from C to E. Then I do the opposite. Put the needle here at B, and then with radius of BD or BF, which is the same as AE or AC, I draw an arc from D to F. So I got this top and the bottom. These are the longer arcs of the ellipse. Now I put the needle at G and use CG or CD, they are the same, and draw another arc, which is this guy, and then I put it at H, and with HE or HF, which is the same as these two guys, I draw an arc from E to F. So the ellipse will be 4 arcs, 2 longers and 2 shorters. And when you connect them together, it should be perfectly accurate ellipse. So it's not approximate, it's perfectly accurate, and that's how you show the ellipse, right? You can do it on the right face, you can do it on the front face, as long as you have what? This touching or tangent rhombus. You can do the rest, right? Okay? So this is how you draw, and for a couple of problems in your homework, you do need to draw an ellipse, and we'll do that in class if you need help with that. Okay, so actually let me show you one on isometric paper here. So if I want to draw, so let's say here I have a let's do the cube again. So this is the cube, right? And let's say on this time, maybe this face, I have a circle that is tangent, and I want to draw that, and let's say it's 4 units by 4 units by 4. Okay, so you draw this right face anywhere. So let's say I go here, and you go a 4 by 4. So this is this face. Then, as I said in the video, you could draw the major diagonal. And the minor, actually you don't really need that, but here you have the midpoints. You connect, right? So you connect this to this, and opposite of that. I can do a little better job. Then you do these guys. And now you start drawing your arcs. So one second. So you come here and then put your needle here, and with this radius you draw the long arc from here to here. Put the needle here and then use the same radius and draw this other long arc. Then put it at this focal point and use this smaller radius here. And then on this focal point and that radius, or this one. And that's your ellipse, okay? And you can get rid of these green lines because you don't need them anymore. Right, so sometimes some quantities do not want to leave. There we go. Okay, so that's how you do an ellipse. Now, in this projection picture, we said that in addition to isometric, which is a group of axonometrics, right, parallels, and orthographic parallels, then we have two other things, Dimetric and trimetric. What are these? So the only difference between isometric, dimetric, and trimetric is the angle of the axes and the scaling. So here, if you remember, the angle between all three axes, x, y, z, was 120, and we used the same scaling on all three axes. Not in Dimetric. In Dimetric, two of the angles are 105 and one is 150, and the scaling on the depth and width are the same, but not on the height. It's a different scale. On trim, and D means 2, so here you have two scales, one for AB and AC, one for AD. Trimetric, of course, 3 scaling, all 3 angles are different, 120, 105, 135, all 3 scaling are different. And you might wonder, why should we do that? Isn't this much easier to do? What's the point? The point is shrinking or stretching apart with different scalings. For example, let's come here and say the thing that you want to create an isometric of is a tall building. So when you want to draw the shape of a tall building, the height is really tall compared to the width and depth. And if you want to put that on isometric view, sometimes even maybe the size of the isometric is not sufficient if you want to do a 1-to-1 scale, or let's say not 1-to-1, maybe 1-to-100, right? Or 100-to-1 actually, 100-to-1 scale for all sizes, right? All dimensions. So scale them all down by a factor of 100-to-1 and draw it. The problem is then probably your width or depth is going to be like 4 units, 5 units, 3 units, or so on. But your height still like, I don't know, 20 units, 30 units, 60 units. So sometimes if you want to show a decent size of the building, so don't make the width and depth super small, then even the size of this paper is not enough, or it's going to be really tall. And in order to avoid that, you might use a smaller scale for the height. So use width and depth of 100 to 1, but for the height, you use 300 to 1. So basically shrink it in the direction of height. Or sometimes you want to stretch something to see some details. So that's the only reason that we might ever see Dimetric, or we barely see any of those ever, and we don't practice on them in this course. But just that's the reason, shrinking or stretching in one direction. Now, in addition to these 3 ways, call them axonometric projections, isometric, dimetric, trimetric, there is another category called oblique projection. And oblique projection has 2 categories, cavalier and cabinet. So what this is, the arrangement of the axes on the paper. So in isometric, if you remember, your height is vertically up and your depth and width are at 30-degree or 120-degree angle, right? In cavalier, that's not the case. And probably you have done that already in your math class or physics class, right? So when you want on a piece of paper to draw X, Y, Z axis, there are probably 2 ways you have seen it in the past that an instructor might draw. One is they do it like this, and then they say this is X, this is Y, and this is Z. Another way they might do it is like this. They say X the right horizontally, Y vertically, and then Z like that, right? So probably you have seen this version too. So this is your isometric view, right? Or if you want more general, you can say this is your axonometric, and this is your what? Oblique. So you keep X and Y as traditional X and Y. You do not rotate X. You keep it as is. Now, what's the point? The point is this. If you have a circle on the XY plane, okay, on the front plane, if you have a circle in oblique, it stays circle because you have not rotated the x-axis or the y-axis. So circles stay circle, while here, any circle on any face is always ellipse in isometric. But here, no. On this face, particularly, it is not going to change. So we don't need to go and draw an ellipse. We can just stick to the circle. And there is one other thing probably that you can see if you look at these two. You see here, I can see the end of the hole. So I can see more in depth because I'm not rotating the part and completely seeing it from a wider angle, so I can see more in depth. I can see the end of the part. Here I cannot. So that's another difference between oblique and isometric. Now oblique, one version is called cavalier, where depth is full scale. Cabinet depth is half scale. Okay, so this is full scale, this is half a scale. And why half a scale? Because again, the part might be too long, like a train, and you shrink the depth to squeeze it all on the same paper. Now you might wonder, what is the angle of this z-axis that you basically show with respect to the x and y? And the answer is this angle here. There are 3 options for it. It can be 30 or 45 or 60. There are 3 options. You can go with any of these angles. Finally, for the 3D views that we draw on a piece of paper, there is perspective, and perspective is Again, we don't really practice in this class obliques, dimetric, trimetric, perspective. We don't do any of them in this class. We just do isometric for practice. But it's just good for you to know about them. So in perspective, which is how our eyes would see the real world, the parallel lines in depth do not stay parallel. They will actually converge to a point on the horizon line beyond which you cannot see, and that point we call vanishing point. Okay? And there are several types of perspective depending on how many vanishing points you're using. One is called one-point vanishing point. Well, all of the depth edges will converge to 1 point. There is a 2-point vanishing point. One group, based on their direction, go to one vanishing point. The other group go to another vanishing point. And then if the height, also the edges on the height not stay parallel, we call them 3-point perspective. In SolidWorks, when you say perspective, that means 3-point perspective. Now, the location of the vanishing point and the location of the horizontal line, or horizon, not horizontal, horizon line, with respect to the part will determine the final shape of the part. So here you can see I'm drawing a table. If I put the horizon line above the table, I can see the top face. If I put it in the middle, I can see the bottom face. Okay, so that will determine the shape, right? So here you can see this box is drawn with vanishing point on the left. Now I, just for your practice knowledge, I put it on the right and redraw it, and you can see the difference. Okay, so right, so this is what I have. And instead of that, I now go ahead and put my vanishing point here. VP, vanishing point. How does it look like if I do that? So the front face of the object, I draw it full scale. Okay, so this face here, this one and this one, the scaling on the height and the width, the scaling is what? 1:1. So I draw it full scale. Now for the depth, there is no specific scaling, okay? So this is arbitrary scaling. So you choose the depth. So this is how I do it. First, I will connect the vertices all to the vanishing point using dashed lines like this. Right? Then I come here and let me draw this with green. So as I said, the front face, no difference. That's the same thing. No difference in the front face. So you're going to get the same thing in green on the top of the black. Now, for the depth, on any of these converging lines, you choose a depth. Again, you can choose as much as you want. And you stop here. Let's say that's the depth that I want. And then from here, you go up, vertically up, if it's a 1-point perspective. And then connect. Then you go horizontally. And then what? And actually this other one we don't need. This one we do not need. Okay, and now you can see the difference between the black box and the green one, right? Which faces you can see. So that's the difference between that's the effect of changing the vanishing point. Now, if you move the horizon line up and down, still the shape will change basically accordingly. So this is just very basic intro to perspective, dimetric, trimetric, cavalier, and cabinet. The intention is not for you to be expert in any of them. The one that you need to practice on for your homework and for this course is drawing an isometric. There are 4 of them in the first part of homework 1. And when we come to class, we're going to practice on them. Okay? Thank you so much for your attention, and I will see you in the next lecture.